Okay, I've got a thumbs up now. The next presentation comes from Nick Tudor, who I heard present at a partner event we ran with the University of Southampton last year. Nick is a business director of a new startup called D-Risk, and of course going to tell us about it shortly. But in his past, he's been involved in software certification for over 15 years, and prior to that, was in aircraft certification for the RAF throughout his career. His Masters in Software Engineering at York was followed with an interest in formal methods. And this sentence has the most number of acronyms I've ever seen. So he is a member of WC71, the committee that wrote ED12C, aka DO178C, with a focus on formal methods supplement as well as the model-based design and tool qualification documents. He is now one of only 4 UK nationals on the invite-only panel and is also the owner-director of D-Risk based in Malvern, which is 10 employees, most of whom are formal methods experts. Over to you, Nick.
I can sing if you want me to. So, right. Enough from the cheap seats in the front here. Right. So, yeah, sorry about the rest of the alphabet that I didn't use in my CV. Right. So, soup to nuts. How do we take from requirements down to ones and noughts? So, a quick overview of D-Risk. A lot of the guys came out of what was formerly DERA, Defence Evaluation Research Agency, and Kinetic. We don't like to mention that bit. We've got a lot of experience across many sectors now. Automotive, working with the likes of Jaguar Land Rover, or a manufacturing group. Automotive, obviously. Aerospace with the Sector Consortium. You heard about that from Mike this morning, and I'd like to thank him for pinching some of my slides. The whole point about this is that formal methods is something that people have been talking about using for years, but you need to have a very large forehead, and you'll notice mine isn't. That doesn't work very well on radio, sorry about that. So you need to have a very large forehead, and you need to really be an expert in how to use formal methods in order to be able to use it. Our approach is that this is something that is very powerful, should be used. You should be able to prove that a 1 and a 0 is in the right order. It's just sums, really, at the end of the day. But it is very difficult maths, so we need to hide that somehow or other behind commercially accessible tools. Tools that the average, without wishing to do anybody down here, but the average engineer should be able to get access to this. So what have we been doing in formal methods? So here's the ego chart. So formal methods in the middle. We're doing everything from requirements, design, source code, object code, and I've called it protocols to sort of sweep up a whole bunch of things which I'm not going to talk about. Requirements, obviously, from my perspective, and apologies to the French and Germans, etc., but it's in English. Then we do everything in model-based design languages like Simulink, Stateflow, SysML, some network diagrams, etc. Source code all the way around, as you can see on the slide. So here's one of the letters that wasn't in my CV, and this is Z, and that is pronounced Z even in America. This comes from the Eurofighter program that we did all the independent verification of the entire flight control system for the Eurofighter aircraft, and we used the Z to do that, and we built a bunch of tools, which I'll come back to in a second. CSP, which is also pronounced CSP in America, stands for Communicating Sequential Processes. And that's come out originally out of Queen's University. Professor now Sir Tony Hoare invented that, and a lot of work being done at Oxford on that. And we do partner with quite a bit with Oxford to make sure this works. And then Hull High Order Logic, which came out of Cambridge. Again, we've done some work with Cambridge on this as well. So that's quite an impressive little CV of stuff that we do in formal methods. The whole point about it is to do verification, and hence why I got invited to come and do this talk. Thank goodness for that, I am in the right place. So what do we mean by verification? Well, the first thing is, well, can I take a design and show that it satisfies its requirements? And we're developing a technology called ModelWorks. More on that throughout this presentation. Clause was the original foundation technology that we developed to automate, as far as we possibly could, the human-based independent verification of the Typhoon flight control law. And that was 350,000 lines of code. Did we find any problems with that? Yes, we did. So they spent north of 100 million quid developing that system and that software. And on one particular day, we found a less than when it should have been a less than or equals. Unfortunately, the pilot found it on the same day in the air, and when he demanded something of the aircraft, it didn't move. Now, in RAF speak, that's what's known as a trouser-filling experience. So 100 million quid to find, to be wrong eventually about something, that's really expensive. Now, it has to be said, I also did some metrics when I was in the Air Force on this, and the error rate on that particular program was 18 times better than NASA considers to be world class. So 100 million quid to be 18 times better than world class, but there's still a bug in it. FIVA then stands for Formal Executable Object Code Verification. It takes object code and verifies it against the source code. We'll talk a little bit about that as we go through. USmooth is a project led by our partner ASV based on the South Coast, and the idea is to develop a decision-making system for an unmanned vessel that will operate over the horizon. You could do this now if you've got deep enough pockets for your insurance. So as soon as somebody realizes that you can ram into a supertanker with one of these things, then good luck. You have to be able to say to an insurer that this is adequately safe. Now, it's got to be out there for a long time. So why there's a market for this of potentially hundreds of thousands of pounds per month for one of these things to operate. What we want to know is this thing going to do the things that another user of the sea would expect it to do? So it's got to comply with something called the Col Regs. This is the rules of the sea. So what standards could we use? There aren't any maritime standards out there for use. So what standards will we use? And at what cost, and in particular, what cost can we enable not just this particular project, but enable the apparently $26 trillion robotics and autonomous systems market to actually be realized? And the answer is, from my perspective, you have to show that these things are safe. If you can't show they're safe, you haven't got a market. As soon as you start killing people at the home or whatever, then you're out of the market straight away. So the problem is, though, you're not prepared to buy a £100,000 Ford Fiesta. You want to spend your £8,000 or whatever it is on a Ford Fiesta. So how do we make this? How do we make this circle square? From my perspective, I have heard this a number of times. Autonomous systems can't be deterministic. What a load of rubbish. Software has got a 1 or a 0 at the end of it. What's not deterministic about that? It's always a 1 or a 0. What you do at the top level is put all the uncertainty into the systems. What you're doing on the outside of that is saying, well, the system itself is deterministic, but the environment in which it operates, which includes to a certain extent the hardware, yes, that's not deterministic. Okay, so there's a reliability, a probability can be attributed to that. What we do is we make things very complex. So having said, here's the physics, here's the environment, we now need to be able to verify this extremely complex piece of software and know that it's actually going to do what we want it to do. There isn't a 1 and a 0 accidentally swapped round somehow or other. So what we're doing is setting the boundary of the design of this particular system and then assuring it from there on in. Software engineering then. So this is the diagram that Mike pinched, but this is the original, because this is what I started to draw back in 2007 when we were doing the full method supplement. There's some extra objectives in there which are about development. This is what you have to produce. And then it all gets a bit messy. This is your requirements bit at the top, back to your system. There's your design going back to high-level requirements. There's some more about the source code. And then there's this bit that goes back from the executable, showing that it satisfies the requirements back to both the design and to the high-level requirements as well. And then we've done enough, apart from the verification of the verification bit, which then says, oh, show me that you've covered everything that you said you were going to do in your requirements, and then show me that the structure of that code has actually been exercised to the extent that we think it needs to be exercised, depending on the level. I haven't got the leveling diagrams here as well. Oh, and by the way, show me that you haven't got anything in there that shouldn't be there, and that's the untraceable object code bit. And that's why I think from a security perspective, doing DO178 is the way ahead, because there isn't anything in here that shouldn't be there, and it does what I say it does. That's it. That's all you really need to be able to show. So there's the soup, and there's the nuts. Ones and noughts as the nuts. From the DO333, this is the formal method supplement. So I've just changed this slightly. You can see all these numbers have changed to FM dot, and that's the full method supplement to DO178. And it's more or less the same, except again over on the right-hand side, you can see that there's less of this coverage, the verification. And in particular, you can see that we've got this laser that's not working. Oh, well, never mind. So you can see there's the one that says structural coverage is done. So that's the one we really wanted to do. We really wanted to hit that one. And we did it, and we showed that you could achieve the same, it would be achieved through doing things like MCDC and what have you. And obviously, we've changed this one as well to do with executable object code. The property preservation thing has gone as well. We also said, right, if you're going to use a formal method, you have to justify why you're using that particular approach, why you're using the right tool for the job. Okay, so it isn't, please just use formal methods. It's tell me which formal method you're going to use and justify it for what you're trying to show against that particular objective. There's a whole bunch of additional objectives that are related to that. So I'm going to remap this because I'm not particularly a fan of the V model or Spiral or Agile or any of that rubbish. I just use something that's simple and straightforward that I can understand. Waterfall model. It's only because it fits on the screen, quite frankly. So we have these objectives that go all the way down about doing the development, and then color-coded, you've got the other objectives on the right-hand side as well. Verification cost down here is 50 to 80%, depending on level, and the development cost is 20 to 50%, depending on level. So we need to do something about the costs. It starts with requirements. We've got to be able to show somehow that what we want this system to do, the software to do, is actually understandable by many people. So those many people include, obviously, you. You're going to be able to write it down and read it again in the future and say, yeah, that's what I meant. You have to give it to somebody else to be able to read it, and you have to, to do the development, and you also have to give it to a regulator. And you could have 3 different mental models of what that says. If the baby don't drink the milk, then boil it. So do I boil the baby or the milk? We need to be very clear about what we mean about this, otherwise accidents can happen. So what we're looking for is a subset of English that we can actually use to actually translate down to a formal description. By that, I can then be very, very clear semantically about what I mean. So we have this program for USmooth. We have this thing called the last response engine. This is known as the oh my god engine. It's when something pops up, instead of waiting for the mathematically intractable problem of path planning, it may not come up with an answer in time. We've got this decision making says that I have to do something. So it's like the bouncing ball jumps out in front of you. Is it followed by a little boy chasing it? You're going to run out, turn out the way. Same thing happens with things at sea as well. So we have system requirements and we have the software requirements. And all we did was we translated that into our subset of the language, enable it to be formalized. That was then reviewed. So that's a manual review process. So you've got to go back to the systems engineer, bless systems engineers, because they don't use this language yet, but there will be a version of this language for system engineers shortly to do with SysML. So now I've got this SRS, I need to do the software design. We did that in Simulink and Stateflow. So the first level of design, how does that work? Well, here's my requirements, here's my system description. You're going to do that design bit. Then you're going to automatically translate this down to CSP. Then you're obviously going to write your own English. At the moment, this is currently manual, but it will be in the process of being automated under Sectair. Take that down to CSP as well. And now we can use the model checker FDR4 to be able to do a formal check. Great. If it all passes, that's fantastic. It just says tick, well done. What happens if you've got it wrong somewhere? Well, we need to pass that back to the user in the language they understand, in this case, Simulink, Stateflow, and obviously to English. And we can actually walk them through and say, this is why there's a mismatch between your requirement and your design. So we can't say that which was wrong, the requirement or the design. It's up to you to decide which was wrong, because it could be either or both. And we get this keyword which is required out of 178, which is independence. So we're independent of the design, and we're independent of the language. We're actually dropping it down to something that's doing the check completely independently of the top two. Now, this process that we're using will be very familiar to you by the end of the presentation, because we're going to use it a lot. And this is what's called a verification tool, or TQL5. That was coincidental. 5 with 5 minutes to go. That's very good. So ModelWorks does that for us. Great. Here's some metrics out of the Picassos program that we were working with Jaguar, Land Rover, Ricardo, Warwick Manufacturing Group. What this is showing is we benchmarked against the baseline in automotive. I'll just show you that we only managed to do 3 in the time available. There's some more work going on with this right now. But you can see that ModelWorks is actually faster than any of the others. And in particular, the one against CL there, that's showing about 60% savings over the benchmark. I'm sorry, I haven't got time to answer questions right now. So 40%, 60% and 30% savings against Simulink Design Verifier. And against the benchmark baseline process, we're talking between 30 and 60%, depending which example. These are industrial examples, and they are repeated 3 times. And I know of no way that this has been done anywhere else in the world. We checked this out with Sectair only last week, and that's true. So considerable time and cost savings here. 52 man hours, that's a week and a half, down to 15, that's a day and a half. And all this is being improved. There's more automation coming down the pipe now as well. So, given I only got a couple of minutes left, what we did next was autocode to C using an off-the-shelf autocoder, often used in automotive. So Simulink autocode code, we produced some formal semantics, this time using Z, as I said earlier, and then using the proof power theorem prover, and using that word independence again, we proved that the code that's produced by the off-the-shelf autocoder, and this is a TQL5 tool, so it's cheap and anybody could use it. So we didn't actually do that yet. That's a thing that's currently in progress, but we've done it for Ada. We did this for the Eurofighter program, so it's not a problem for us to be able to do this. Trust me, I'm not a doctor. Executable logic code verification. This is where it gets interesting, perhaps. So we compiled it to an ARM chip. Great. So here's Fever, again, very similar diagram. Compiled it. This time what we have is the instruction set architecture formalized in Hull. So all we're doing is picking up each of those Hull descriptions and comparing them against the similar description we have in Hull for the source code. And again, you get that independence word. This is still work in progress, but we did it for one specific C function in the middle of last year. This is ongoing work. So given that we can do that automatically in the future, then we get that tick as well. The final thing is this coverage thing. So by all means, go and pick up DO333 and read this, but it basically says if you've got formal descriptions of the higher level artifacts above the executable, then you can claim all sorts of things to do with executable object code. It does this, in fact. It says, come on, anything with a formal representation in red is what we do, of course. So that's design is, of course, the source code is, and the executable. So that means that we can claim Fever at this point down here does the verification against the source code, Clause does the design, and ModelWorks does the high-level requirements. So we can make that previous slide and meet the objectives. So how do we meet the coverage? Well, as a byproduct of doing this, then we get the coverage as well, and that's what that particular objective is all about. So that's a byproduct. You don't have to do anything extra. Costs, then. So look to the cost slide just for ModelWorks, of course. The IP, as far as I'm concerned, from a UK PLC perspective, the intellectual property is in this area. It's not down in the source code and the design. That's just merely laying bricks. Okay, it's the architect who designs your house is where all the value is. So what we want here is to make sure that IP stays inside your company, and that's what Mike talked about earlier with Sectair. It needs to be retained inside the company that owns it, sort of giving it away. So the verification against design against requirements, that's automatic. So you don't get quite all. There is some skipping across the peaks here rather than diving into the valleys, but there are some review aspects required. It's not quite fully automated. Then you get the next bit, of course, the table A5 with clause. Similarly, claims and objectives are partial there. And similarly with their executable, there will be some where it's appropriate to do so, manual steps. And of course, you get that coverage as well. And that means you get significant cost savings. And I enjoyed doing that animation. That's quite fun, actually. So I think I'm just about on time. So from an unmanned systems perspective, decision-making systems, yes, we can do those now. And the version 2 of this is going out, probably going to test in the Solent. So if you want to avoid the Solent during the summer, by all means do. I might be on that boat. Never mind, we'll see. We're testing this over the summer. Business cases for wider adoption of these tools is on the speed of which you can do it and the cost of the tools. We'll be looking at doing a demonstration later this year, but also expanding this use into other areas as well, including swarming and automotive, aerospace and security. I'm happy to take half a question, but nobody from Intel's allowed to ask because he always asks a question. So, thank you.